A round cone with half angle alpha is equal to 30 degree and radius of the base r is equal to 5 centimeter rolls uniformly and without slipping over a horizontal plane as shown in figure. So here we have this cone and it is rolling in this plane, and this is the center of the cone and this is the apex of the cone. The cone apex is hinged at point O, which is on the same level with point C, the cone base center. The velocity of point C is v is equal to 10 centimeter per second. Find the moduli of the first part, the vector of the angular velocity of the cone and the angle it forms with the vertical, and in B part the vector of the angular acceleration of the cone. Now this is our cone and it is rolling, and let it is rotating about this axis. Let this is x-axis and let this is the angular velocity omega. Clear? And r is its radius. R is the radius of this cone. This point C and this point O are in the same level, and let this is y-axis and let this is z-axis. Clear? Now this is rolling in this plane. Now suppose that it has a velocity in this direction. Clear? So what we have to find out here, we have to find out the vector of the angular velocity of the cone. Now if you observe carefully, this cone is rotating about this axis, means the axis of rotation is x-axis here, and also it is rotating about this y-axis. So it has two angular velocities, one along this x-axis and one along y-axis. Clear? So the angular velocity of the cone must be the vector sum of the angular velocity along x-axis. Let this is omega 1, this is omega 1, and along y-axis let it is omega 2. So the angular velocity of the cone is equal to the vector sum of these two angular velocities. Now what are the values of omega 1 and omega 2? For this we have to consider its motion. Now this cone is rolling, and from the concept of rolling we know that v is equal to omega r, and from here we can write omega 1, and that is equal to v by r, and the direction of omega 1 is along x-axis, so here it is I cap. Now what about omega 2? Now for omega 2 we can write it as v, this v divided by OC, this length OC. Clear? And direction is j cap. Now from this geometry we can write that this OC is equal to r cot alpha. This OC is equal to r cot alpha. So from here we have omega, and that omega is equal to v by r I cap plus v by r cot alpha j cap. Clear? So this is the angular velocity, and what we have to find out, we have to find out the moduli of this angular velocity vector. So the moduli of this is equal to under root of v by r whole square plus v by r cot alpha whole square, because both these angular velocity components are perpendicular to each other. So from here finally we get v by r secant alpha, and finally by putting the value of V is 10 and R is 5, secant 30 degree, and from here we have the value of the moduli of omega equal to 2.3 radians per second. Clear? Now in the second part of this part A, we have to find the angle which this angular velocity makes with the vertical. So you have to be careful. He is asking about the angle it makes with the vertical. So this is the direction of omega 2 and this is the direction of omega 1, and its resultant, that is omega, is in this direction, and we have to find this angle. Clear? So let this angle is theta. So from this figure we can write tan theta, that is equal to omega 1 by omega 2. Now for omega 1 we have this result, and for omega 2 we have this result. So from here we can write V by R divided by V by R cot alpha, or you can write 1 by tangent alpha, and alpha is 30 degree, so tan 30 degree. So from here we have under root 3, so we can write theta equal to 60 degree. Clear? Now in order to solve this B part, we again consider this equation, the equation for the net angular velocity. From here we can write this omega equal to omega 1 plus omega 2, and if we differentiate it on both sides with respect to time, now from here we get beta, that is the angular acceleration, and that is equal to d omega 1 by dt plus 0. Now why this is 0? Because along this y-axis the direction is not changing and neither the magnitude is changing, hence this omega 2 is constant as the cone is rolling about this y-axis, so its derivative is 0. Clear? So only thing we are left with is variation in this omega 1, and here the magnitude of omega 1 is constant, but the change in it is because of the change in direction. Clear? So let at any instant of time, this is the direction of omega 1, and let it makes an angle phi with x-axis. Clear? It makes an angle phi with x-axis because it is rotating about this y-axis, and this plane is naturally xz plane. So at any instant this omega 1 suppose makes an angle phi with x-axis, means the initial axis of rotation. Clear? So we can write omega 1 as omega 1 cos phi I cap plus omega 1 sin phi a cap. Clear? So if we put this value of omega 1 here, we get beta, it is equal to d by dt omega 1 cos phi I cap plus omega 1 sin phi k cap. Clear? And if we differentiate it, we get minus omega 1 sin phi d phi by dt I cap plus omega 1 cos phi d phi by dt k cap, and from here we can write beta, and that is equal to minus omega 1, and this d phi by dt is omega 2 here, and this is sine phi I cap plus omega 1 omega 2 cos phi k cap. Clear? So you have to be careful that here d phi by dt is basically omega 2, because the cone is rotating about this y-axis, and as this cone rolls on this plane, so the variation is with respect to y-axis. The angular variation here we have to count with respect to y-axis. Clear? So from here we can write the magnitude of beta. The magnitude of beta is equal to under root omega 1 omega 2 sine phi whole square plus omega 1 omega 2 cos phi whole square, and from here we can write omega 1 omega 2, and we have calculated the value of omega 1 and omega 2, and from our previous results we can have v square by r square tangent alpha, and from here we get, by putting the values of v, r and tangent alpha, so finally we will get beta equal to 2.3 radians per second square. Clear? So this is our result to part B.